can see. Your assignment tonight is to finish Lab 10, which we're going to do in class next period. Before we go over this assignment, I would like you to turn back in your packet to page 18. We were not quite done with question 7. I'd like to get through that with you first, and then go back to question 2, which we skipped, and then we will move on to going over the assignment that was due today, okay? So let's all turn to page 18 in your packet, and let's finish going over this. So yesterday in question 7, we left off by determining the time it took for this projectile to land. We recorded it in the chart. So let's go right on to part B. Part B is asking for what? Who can tell me? What is part B asking for? Chaudhry? VIX is correct. So that means we're going to cover up the Y column. What equation, Juan, can we use to help us get VIX if we're only looking at the X values? Yep. Devin, what's going to cancel out because we're working in the X direction? Nope. VI is what we're looking for, so it can't cancel out. Yeah, because the A is 0 in the X direction, so we're left with D as VIT. Now you got to move it around and solve it for VI. Nikolai, what's that equation for VI going to look like? That's right. So to get that value in the X direction, we're going to substitute in the X displacement, which we have, that was given as 80 point meters, and divide by the time we found in part B, which is 2.7 seconds. All right, so let's keep going with this. So let's go ahead and solve that out, getting an answer with proper units and sig figs. And Alex, can you tell me what that answer is going to be? Almost. Jacob, can you tell me what he's missing? Yeah, the point. Good, Alex. 30 point meters per second. It needs 2 sig figs. That answer can now come up into our chart. We see the chart is completed. However, there is a part C. So let's see if we can figure out what part C is asking you to find. The vertical velocity of the ball just before it hits the water's right where it's hitting the water is out here. Ryan, any idea what we're asking you for? No, we have the VIY. We're not asking you for that. And the water is not up here. It's down here. Gianna, can you help them out? Nope. There's the word velocity here. So, Vince? In the Y direction. We are asking you to find VF in the Y direction. Since I'm looking for something in the Y direction, we ignore the X column of values. Cindy, any idea what equation we could use to get a VF? That is correct. Now, since we are working in the Y direction, something here, Miriam, is going to cancel out. What's going to cancel out? That's right, because the VI in the Y direction is 0. So we're just looking at VF in the Y is A times T. We can now plug in the vertical acceleration given to us. We know this is on Earth, so it's negative 9.81 meter per second squared times the time we found, 2.7 seconds. And let's go ahead and solve that. Kara, any idea what that final velocity in the Y is? Okay, Janicia, can you tell me what that final velocity in the Y is, please? Very good. Negative 26 meters per second, and that is the last part of that. Let's go back to question 2, which is on page 14, and then we'll go over the homework. So question 2 says that we have a ball being projected horizontally off the top of a 50 point meter high cliff at a speed of 5 meters per second. I want to know what horizontal distance the ball travels in just the first 0.1 seconds. So if I make a sketch like we always do, here is that initial velocity of the projectile horizontally. It's coming down and out, landing on the ground in a time of t. There is our horizontal displacement. There is the vertical displacement. Now, what we can see is that 50 meters would be the height of the cliff, which is here. And 5 meters per second would be the VI in the X direction. Now, before I go ahead and label the time down here as a tenth of a second, I want you to think if that makes any sense. Is it going to actually get to the ground in the tenth of a second? So let's think about that. Remember that the ceiling in this classroom is about 3 meters. This is going to go 50 meters. When you did your reaction time lab, all of your reaction times were in the neighborhood of a tenth of a second. Would the meter stick have fallen 50 meters in a tenth of a second? No, it was falling just about that much in a tenth of a second. So that means this is not where the time in the question is. We're going to end it somewhere up here where that time is a tenth of a second, which means the dy would be just that little piece right there. And the dx would be just that little arrow right there. So I'm adding a couple of additional arrows to this where I'm not looking at the full height, nor am I looking at the full range. Let's go ahead and make our chart for what we know about the x and the y directions. In the x direction, Kiara, the acceleration is always meter per second squared. Ryder, what is it always in the y direction for Earth? Good. Let's now do our VIs. In the X direction, Gavin, what is the VI for this question? That is correct. And in the Y direction, Haley? Excellent. Okay, now we can go to the Ds. Do I know what the D in the X direction is? This little arrow, Emma. Do I know that? Nope. So it's a question mark. Do I know what the DY is, that little arrow there, Blake? Nope. So that is a question mark. And finally, I add my T's. Do I know what the time is to this point, Shelley? That's right, 0.1 seconds. All right, so what is it that I am asking you to find here? What is it, Jackson, that I'm asking you to find? So how do I write that as a symbol? Because I don't want to spell it out. dx is correct, which means I'm going to ignore the y column since I already have the time. Max, can you give me an equation that I can use to find that using the A, the VI, and the T? That is correct. We're going to simplify it because in each direction, something's going to cancel out. Elisa, what's going to cancel out in the X direction here? That's right, because A is 0, which means that the D is VI times T in the X direction. Let's go ahead and do our substitution with units. So the VI in our X direction, we said was 5 meters per second. The time that we were given was a tenth of a second. So, Chaudhry, what does that mean the range is? What is a tenth of 5? Oh, we should know how to do that math in our head. A tenth of 5. What is 1 times 5? 0.5, yeah, right? Okay, 0.5, and that gives you meters. 0.5 meters is our answer. I'm going to go ahead and put that in the chart. Now, do I have to come up with the dy? No, because it didn't ask for it. So you don't always have to completely fill out the chart. All right, let's go over the homework pages 19 and 20, please. Pages 19 and 20. Okay, let me just give you the answers, and then we'll see if you want me to go over any of it with you. So in number 1, part A, the time is 9.99 seconds. In part B, the range is 2.00 times 10 to the 3 meters. In number 2, the final answer is 132 meters. In number 3, the final answer is 1.7 meters. And in number 4, the answer is also 1.7 meters. Do you want to go over any of those?
I do have a question.
Yeah, I am.
So for number 1, I did 10 seconds.
No, because we know that the displacement had 3 sig figs, and so does the acceleration of gravity. 3. 10 does not have 3 sig figs. Yep.
Go over 1A.
Sure. So in 1A, again, I'm going to start with my sketch. Here is my sketch. I see the dy, the vi in the X direction. I'm looking for the time. Here is my chart. So I'm showing the A's, the D's, the VI's, and I'm looking for the T. So to get the T, I'm going to use the Y direction because that's where I knew more. I had the A, the D, and the VI. So D is VIT plus half AT squared. So the time becomes the square root of 2D over A because the VI in the Y direction is 0. We're now going to plug in square root of 2 times negative 490 point meters because it did go down 490 meters, not up. And then divide that by negative 9.81 meter per second squared. Take your square root, and with 3 sig figs, you get 9.99 seconds. Anything else you want to ask about on the assignment, Miriam? 1B. All right. So now I want your D in the X direction. So I'm going to use the same equation. D is VIT plus half AT squared. The half AT squared drops out because the A in the X direction is 0. So I'm going to take the initial velocity in the X direction, which is 200 point meters per second, multiply it by 9.99 seconds. I need 3 sig figs. The only way to get my answer with proper sig figs is to put it in scientific notation, giving me 2.00 times 10 to the 3 meters. Anything else? Kiara? Yep. Number 2. So here is my sketch. I knew the dy, the VIX, the dx, and the t are unknown. I'm going to go ahead and make my chart. I've got my A's. I knew the D in the Y direction was negative 176.4 meters. My VI in the Y is 0, and the X, it's 22.0 meters per second. First thing I got to do is find the time in order to find the D in the X direction. So to do that, I'm going to use the Y direction because that's where I know more. The D is VIT plus half AT squared. The VI times T drops out because in the Y direction, VI is 0. Giving us the equation for time, which is the square root of 2D over A. In the Y direction, we do the square root of 2 times negative 176.4 meters over negative 9.81 meter per second squared. I need 3 sig figs because of the acceleration of gravity. That gives me a time of 6.00 seconds. I can now put that in the chart for both columns. Now to get D in the X direction, I'm going to do D is VIT plus half AT squared. In the X direction, half of AT squared drops out because A is 0. So I'm just going to do 22.0 meters per second times that time of 6 seconds with 3 sig figs gives me 132 meters. Yep. So here is my chart with my VIX, my DX. I don't know DY or T. Here's my chart. I'm looking for the DY in the question. So first thing I do is come up with the time. In this question, I know more in the X direction. I know the A, the D, and the VI. I do not know the time here. This is where my unknown is. So what I'm going to do is use D as VIT plus half AT squared to come up with the time in the X direction. So since the half AT squared drops out, my D is VIT. So the time is D divided by VI. That is the range of 0.75 meters over 1.27 meters per second gives me a time of 0.59 seconds. Now that can go back in the chart. And now I can use that in the Y direction to get that D value. Using D as VIT plus half AT squared, the VIT drops out because VI in the Y is 0. So half of negative 9.81 meter per second squared times 0.59 seconds, which must then get squared, gives me a displacement in the vertical direction of negative 1.7 meters. But height is never a negative quantity, so the height is just 1.7 meters. All right, I am not going to do number 4 for you because that would have meant I did the entire homework for you in 5 minutes. I'm not going to do that. All right, questions? All right, you may use your homework, your reference table, and your calculator to help you with the quiz today. Let me hand it out. It is a show work quiz. Please follow the directions at the top of the quiz. Good luck. Is dead. Show it to me that it's dead, and then I'll get it. No talking. Good luck. What?
I have a calculator.
Still dead? Okay. Tomorrow I'm not going to give you one. You need to get it charged or tomorrow.
I'll do that.
But you can get started on the quiz first because the calculator is the very last thing you need. Just follow the directions at the top of the quiz.
I didn't get it.
I didn't give you one? Sorry. That I can't give you that. You have to just bring it to show me. When you are done with the quiz, please raise your hand. I'll come get it from you. You can only look at your homework. Let me give you your quiz to take. When you're done with the quiz, raise your hand. I'll take it from you. Give you 1 more minute to wrap it up. 1 minute. All right, let's wrap it up. I'm going to come and get your quiz. I think I got everybody in the back row. Is that right? Yes? Okay. Please, when you're done, we'll just bring it up. Okay. All right, let's move into section C. And you need out your notebook as well as the other materials that you had out for your quiz. We're going to talk about our last section of Unit 5 today, which is about now a different type of projectile that we're going to fire at an angle to the horizontal. Just like what I asked you to do for today, you'll have to use vectors, graphs, and equations to describe how these types of projectiles move. We're also going to do another conceptual piece talking about how the launch angle affects the hang time, the range, and the maximum height that these projectiles spend moving. And then we're going to solve some problems, lots of problems. All right, so let's talk about what we mean by an angled projectile. What is an angled projectile? These are projectiles which get launched at an angle to the horizontal. So they are not coming off the top of a cliff horizontally. They're on the ground and they are being launched at some angle to the horizontal. And this is what their trajectories end up looking like. Notice that we end up forming a parabola where the projectile starts on the ground and ends on the ground, but it's going up and out, up to the peak, and then at the peak it starts to come down while it's also going out, giving us a symmetrical type of motion around the peak. So as we see here, it's rising upward to the peak while it is moving outward horizontally. And then once it reaches the peak, it will start to fall down with a motion which is symmetrical to the upward path. Essentially, what you had to do for today was solve problems from this highest point coming down. Now what we're going to do is start at the ground and it's going to go up first. And then we'll deal with the downward path like we did for today. The typical kinds of things that I could ask you to solve for these types of projectiles are things like the hang time, the range, just like we did for the horizontal projectiles. But also now I could ask you, how high does it go? How high does it go in the air? Before Thanksgiving. But this is the last section. So next week, we're going to be spending a lot of time doing labs. Okay, so let's talk about now the effect of changing the launch angle on the projectile's path. So first of all, I want you to understand that when I'm talking about the effect of the launch angle, I need to not change the velocity, or rather the speed of the projectile as it comes out of the cannon. Think of shooting a cannonball out of a cannon. So the initial speed of our cannonball is going to be fixed. We are not going to change its value. What I want you to notice here is that when I look at these projectiles, I can see that as I increase the launch angle, something happens to the amount of time it's in the air, its height, and its range. So let's look at these three here. I'm showing you three common launch angles, 30, 45, and 60 degrees with the horizontal. As I increase the launch angle, what happens to the amount of time it spends in the air? You see how they're all being fired simultaneously? As I increase the launch angle from 30 to 60 degrees, what happens to that hang time? One? Yeah, it increases. Okay. And in fact, notice that the 60-degree angle is the one that's spending the most time moving. It's still moving while the other two have already landed. So the closer I make my cannon's barrel to 90 degrees, where now it's shooting it straight up, the longer it will spend in the air. Now let's talk about the range. Look at all three of these. Remember, range refers to the horizontal distance that it travels. Which one of these travels the greatest horizontal distance? Vincent? 45. And that's because it's exactly halfway between 0 and 90. So we're putting a good chunk of its velocity in the horizontal direction as we are in the vertical. So because it has a balanced horizontal and vertical velocity, it can go out the furthest. Now, which of these has the longest or the highest height? 60. And that's again because it is spending the most time moving up against gravity. So the longer it spends going up, the higher it will go. So what we're noticing here is that our maximum range always occurs at 45 degrees, provided we are launching and landing on the ground. If I were to launch it from the top of a cliff at an angle and then have it land on the ground, that would not be the case. But what we're going to limit our discussion to in this course is launching and landing on the ground. These are angles you're just going to be asked, what angle is it? So these are just angles you have to know. At 45 degrees, we will always get the maximum range. We will always achieve our highest height if I shoot it straight up. So that way all of the velocity is acting against gravity. And when I go higher, of course, that means I can spend more time in the air. So the longest hang time will also occur at 90 degrees. Now, there is something else quite unique about the 30 and 60 degree angles. I want you to look at their ranges, 30 and 60 degrees. What do you notice about the range of the 30-degree projectile and the 60-degree projectile? What do you notice about them? The range. What do you notice? Can you see it? They are the same. That's right. There is something very special about 30 and 60 degrees. Anybody know something about 30 and 60 degrees? 30 and 60 degrees are called complementary angles. Do you know what that means? You learned about that in geometry. What does that mean, Ryder? They add up to 90. Anytime you have launch angles which add to 90, in other words, they're complements, you will always get the same range. It's another pattern that you need to know. So whenever we have complementary angles like 30 and 60, they're going to land at the same position. They will have the same range. So what other angle would have the same range as 70 degrees? What is it, Blake? 20. That's right. What if I launched it at 50 degrees? What other angle would produce the same range? 40. That's right, because they are complements. That is a pattern that you need to know for a test. And you can see that here. If I did it at 80 and 10, notice that 80 degrees and 10 degrees are both landing at the same position, where 45 will always make it go out considerably further. That is the farthest range you'll get. All right, so let's talk about how we're now going to solve problems involving these types of projectiles, the steps, and the different kinds of motion that we see. So when I deal with an angled projectile, remember that the motion has both components in the vertical and horizontal velocity. These projectiles do not have an initial velocity of 0 anywhere. They don't. If they start off with an initial velocity of 0, they're only going to go down. These have to go up first, which means their horizontal and vertical velocity components are not zero. Remember that these types of projectiles we're studying in Unit 5, all of them are moving both horizontally and vertically simultaneously. And since the horizontal and vertical motions are perpendicular, they will be treated separately because they are independent of each other. So just like what we saw with our horizontally fired projectiles, we're going to use two completely separate and distinct sets of equations. One set that applies to the horizontal direction of motion and one that applies to the vertical direction of motion. And that's because the projectile is doing something different in each direction. Bless you. Bless you. We all set? Yes? No? Yes? Okay. So let's talk about what's happening in each direction. Remember, in the horizontal direction, doesn't matter that this is now an angled projectile, that's our gravity-free path. So the horizontal motion of a projectile can always be described as having a constant velocity. Since it's moving with a constant velocity, that means one of your givens will always be the horizontal acceleration value, 0 meters per second squared in the x direction. Is that any different than the last type of projectile? No, it's exactly the same number in the same direction. The description of motion is exactly the same. The vertical direction is where we have a slight difference. In the vertical direction, we're still going to have a constant acceleration, which comes from gravity, which is dependent on the planet you're on. But because it's going up first and then down, we're not going to have a VI value, which is 0. Instead, this time we can only talk about the acceleration in the vertical direction being negative 9.81 meter per second squared if we are on Earth. Just like what we talked about with the projectiles that we threw up in the air, on the way up, we see the same motion as we do on the way down. They're at the same heights at the same times on either side of the peak. That is true here too. We have that symmetry of motion in the upward and downward paths. The only difference is that with the upward path, the velocities are positive. On the downward path, they are negative. And at the peak, what is the vertical velocity? 0. That's right. It's got to stop going up so it can start coming down. So let's talk about how we will therefore analyze the initial velocity that's given to us. We are going to have to figure out, if it's not told to us, what the initial velocity components are in the x and y directions using trigonometry. Generally, what we do is we tell you the launch speed and the angle of the barrel of the cannon. That's it. You can't use that speed and the angle to solve the problem. You have to go one more step to figure out what VIX and VIY are using trig. So here's how you find the initial x component of the velocity, VIX. And this is where we're going to check things off. We have new equations to check off on page 6 of the reference table. To get the initial velocity component in the x direction, we're going to use this equation on page 6 of our reference table, which says AX equals A cosine theta. You can go ahead and check that off. AX is A cosine theta. Now, in the right-hand column, notice that the capital A, we'll check that off, stands for any vector quantity. So I could actually use this to find the X, or horizontal component of any vector, like displacement, velocity, and acceleration. Those are the three vectors that we know about so far. And the angle theta, which I'd like you to check off at the bottom of your reference table, theta is the angle, and that will always be measured in degrees. So let me show you what you should have just checked off to make sure you're doing it right along with me. So on page 6 of your reference table, you should have just checked off that equation. AX is A cosine theta. You should have checked off the capital A, standing for any vector quantity, like displacement, velocity, or acceleration. And then you should have checked off the angle theta down here, and that will always be measured in degrees in this class. Okay? Now, that will help you get the horizontal component. We not only need the horizontal component of the launch speed, we're also going to need the vertical component of the launch speed, the initial velocity in the y direction, VIY. It is not 0 in these types of questions. If it's 0, what is the projectile going to do? Is it going to go up? No, it can't. You're not giving it any oomph to go up. So the VIY cannot be 0. To find this, we're going to use the equation AY equals A sine theta. Please check that off on your reference table. That AY is A sine of theta. So we just checked off 2 more equations, which we now use with these types of projectiles. All right, let's take our break. And when you come back, I've got like 2 more slides, and then we're going to start our lab on our Chromebooks. With your what? Do you have a free period today? I can do 7. I'll be in the physics office next time. Next door. Across the hall is the Pays Lab. Pays Lab. It's for our special ed students who get occupational therapy.
Oh, you made something wrong. Yeah.
How'd she do last night?
I think she had a sick night. We had her in with the ulcer first. Quarter to 1, and I moved her to her room.
She probably needs her home.
So she was so tired this morning. My wife took her up to bed with her. She slept the rest of the time. So
Yeah.
she's doing good. We'll send you
She's always,
photos.
she's always had her own crate. So
Oh, does she?
yeah,
Oh,
she's
okay. So
always
we
had-
didn't know.
If you
Okay.
get a crate, I can
No,
give
no,
you
no.
one for her
We've got
until she grows out of it.
Right now we've got 3, and we've got a 4th large crate too. So like we have like a kitchen island.
Yeah,
Deb made like a kitchen island out of it.
Yeah.
So there's 3 there now, but we got another big crate that she can go into. So.
She probably doesn't need a real big one yet.
It's funny though, we put her in a little crate and she just barely
You know, that would be good because she was
safe space.
say, well, plus she was having a hard time.
She
Maybe
actually,
outside so much while she would go to the bathroom in the crate.
she's been great. I've taken her out. She does all her business outside. Even quarter to 1. I mean, she just went a little bit.
Okay.
I like them
Yeah,
to
plus-
interact a little
plus-
more than they are now, but it's kind of,
Well, no, that's
You know.
okay. It's gonna take her time to get used to
but
everybody.
we'll send you photos. And we'll try to get a family, we'll try to get some
And if
family
you
photos.
can,
Right now-
let me know and
No,
I'll
no,
come
no.
to your house and take
Yeah,
a
you
picture
can
of
come over.
guys.
That's fine. That's great. That would be great. It's just she didn't sit still a lot. So even this morning,
Well, that's
after
what
she
Gail said to me last. night.
after
thought
she ate-
was kind of shy. She didn't want to get.
after she ate, because in the morning I usually give them a cereal and and then a roll. But what I did was I just took some additional food of hers, and as I'm giving them stuff, making sure she gets something too. And she takes it so soft.
Yeah, I know.
So
She's such a gentle dog.
She's good. She's good. It's just gonna be a tough couple
It
of
always
days.
takes a dog time to acclimate.
She actually marched through the yard this morning in the dark, which was pretty good because the other dogs were out there. Because she didn't stray far. I almost think I could take the leash off her, just let her out and let her back
Probably
in because
can now.
she'd rather come back in. She's more afraid of. I think she's more afraid of being out there by herself. Okay. Sorry,
That's awesome. No, you're not bothering me. You can always talk about Gemma. All right, so let's finish this up. So now let's talk about how you're going to solve problems for these. And tomorrow you're going to spend the period working on solving questions. So the first thing you're going to do, like we did with the horizontal projectiles, is make a sketch. You're going to start like we did with the horizontal ones, making a sketch. The sketch is not going to look the same because these projectiles are not being launched off the top of a cliff. But you will make a sketch. Then, and I'll show you that in the class tomorrow. Then what you'll do is use the given value for the initial velocity, meaning its launch speed and angle, to determine what the horizontal and vertical velocity components are, what the VIX and the VIY are, because you're not going to be told what those are. You're going to have to figure out what they are using those two equations that I just gave you. AX is A cosine theta and AY is A sine theta. Once you've done that, you can now make your givens table with what you know about the X direction in one column and what you know about the Y direction in the other, just like we kind of were setting it up for the horizontal ones. So these can actually go a little quicker because you've got some familiarity with this process. The only thing that's different is now coming up with the VIX and the VIY first after you've made your sketch. So I'll wait for you to get this down because then there's those two other steps, just like we were, or three other steps like we had for the horizontal ones. And then we'll put our stuff away and just go right to the lab on our Chromebook. Okay, so step one is sketch. Step two is find VIX and VIY using AX is A cosine theta and AY is A sine theta. Then you're going to list your givens in the table. Okay, fourth step is to identify the unknown. What is the question asking you to calculate? What is the question asking you to calculate? This is just like what we did yesterday, right? What did we do after we identified the unknown? Do you remember? What did you always have to know? Janicia? And you're going to have to get that time again. Before you can solve for anything else, you need to know the time it spends in the air, the hang time. So you're going to use the same process. What do you know about the X? What do you know about the Y? Where do you know more? Wherever you know more, the X or the Y, that is the direction of the givens you're going to use to help you get the time. And then once you have your time, you can now solve for your unknown because the time in the X and the time in the Y are the same. Okay? So your homework tonight is to really study these notes so you understand that process. So that way tomorrow when we solve questions, we can start off going pretty quick. You know what you have to do. You're just not sure how to get it done yet because I haven't done one for you yet, but I'll do that tomorrow. Okay? All right, please put everything away except your Chromebook. And once you have your Chromebook out, go ahead and open up the lab assignment, Lab 10. You will need nothing else for the rest of our class today. Lab 10, I think you should be able to complete it with me during class if you follow along. If you get behind and it's not done before the end of the class period, you do need to complete it for homework, and it needs to be turned in before tomorrow's class begins. Otherwise, it will count as a late lab. And as you know, late labs lose half credit right off. So if you end up getting 7 out of 10, that's not what's going to show in Aspen. It's going to show as a 3.5 out of 10. And those late points you can never get back. All right, so I'll give you a minute to get your Chromebooks out and open. And once you have it out and open, go ahead and open up the lab 10. It will look like this lab that you see here on the screen. All right, so as we work on this lab today, you'll see that linked to the lab is a simulation. Go ahead and click on that simulation for projectile motion, and I'm going to walk you through setting it up. All right, so once you've opened up the simulation, I want you to click on the Intro tab. And we have to make some adjustments here. What we're going to do, according to the Google Sheet, which is, hold on a second, there we go. According to the Google Sheet, we want to set the parameters so that way the height of the cannon is 10 meters and the launch angle is 0 degrees, okay? So let's go ahead and make sure that's what you have set here in this projectile motion lab. So notice that my cannon is, when I opened it, it already gave me 10 degrees. And you see here on the cannon, it says 0 degrees. I've got the 10 meters and the 0 degrees. That's all set. Okay. Now we can go to part 1 of the lab. So let's click on the part 1 tab at the bottom, where we're testing the effect of changing the initial speed on these projectiles. All right. So look at what we're going to do here. It tells us right at the top to adjust the cannon's initial speed to the following parameters. We will then fire the cannon at each of these speeds and then record the appropriate hang time and range in this data table. Now, to measure the hang time and the range, we're going to use a blue measuring tool. I'll show you how to do this for the first one. So notice we're going to keep the height for each of these at 10 meters. We're going to start off with an initial speed of 2 meters per second. So let's do this together. In the simulation, please set the initial speed down here on the bottom left to 2 meters per second. You can adjust that with the slider bar. There it is, 2 meters per second. Now you can click the launch button, which is this red button. That's going to fire it. And you can see that it went right down to the ground and landed there. Now, up here on the top right, this is our blue measuring tool. Go ahead and click that. And I want you to bring it down and put it on the point where that pumpkin landed on the ground right there. And you'll see that when you do that, you see how it lights up yellow? That's the point you're looking at. Now, it's giving you the things we need, like the time and the range. So notice that my time was 1.43 seconds and my range was 2.86 meters. Is that what you're getting on yours as well? That's a confirmation that you are in the right spot. So let's go back to the lab and type these in. The hang time was what? 1.43. We're not going to put the units, otherwise the Google Sheet won't be able to do the graphs that we need. And what was the range? 2.86. Go ahead, type those in. Now let's do the second one together, and then I'm going to give you 2 minutes to get the rest of the data yourself. Let's now change the speed to 4 meters per second in the simulation. So I'm going to just increase this to 4. I'm going to move the blue measuring tool out of the way, and I'm going to fire it. I'm going to bring that blue measuring tool down to the ground, let it light up at the ground. There is my time and my range. I'm going to take those numbers and put them in my Google Sheet. Okay. Did you get 1.43 for the time and 5.71 for the range? Yes? Okay. Take a minute and get the rest of those now on your own for this table. Notice we're just increasing the speed by 2 meters per second each time. Who's still working on getting data for part 1? Okay, I'll give you another minute. We're not going to make the graphs. So if you finished part 1 with the data table, just hang tight. We are not going to make the graphs next. Okay, once you have your data in part 1, we're going to go to part 2. Click on the tab on the bottom, which says part 2, effect of height. What we're now going to do is go back into our simulation and reset the cannon speed to 15 meters per second and adjust the height to these values. Notice that in part 2, we're going to keep the speed constant in every trial, 15 meters per second. So let's adjust this in our simulation. So the way we can reset this, folks, is down here on the bottom right. You'll see that there is this reset button in orange. Go ahead and click that. That clears everything out. I want you to click on the cannon and drag it down until the height is 2 meters. It's frozen? I'm sorry. There we go. So let me redo that. Click on the reset button on the bottom right. Then click on your cannon and drag it down until the height is 2 meters. You are not going to change this initial speed at all here in this part of the lab. Go ahead and fire it. And then what you're going to do is grab your blue measuring tool, bring it down, measure the time and the range when it hits the ground at 2 meters. So we should have all gotten 0.64 seconds and 9.58 meters. Did you get that when you did it yourself? That's a check to make sure you're doing it correctly. So 0.64 seconds, let's type this in. 0.64 seconds, and what did I say the range was? 9.58 meters. Notice that in the next trial, I want you to change the height to 4 meters. So let's go ahead and do that. Here, you're going to raise the cannon up to 4 meters. Move your blue measuring tool out of the way and hit fire. You can now bring your blue measuring tool down and measure the time and the range. All right, let me give you now a couple minutes to finish this data table, okay? Go ahead and finish off this one. You're just changing the height by 2 meters each time. Once you have all of that data, you can close the simulation. You will not need it anymore. And then I'd like you to go back to part 1. And we'll make these graphs together because they will not show up the way we want. There's a lot of stuff we have to click and get to customize. So you'll want to follow along with me on making these graphs. Yes. Anyone need more time to get the data for part 1 or part 2? You're on the last one? Okay. And then the rest of us can go back to part 1. Good. Anyone still need more time? Okay, let's work together. Part 1. In step 2, in part 1, it asked you to make a graph of the hang time versus the initial speed. Let me show you how to do this. We are not going to select the whole chart. What I want you to do is take your cursor, select the cell where it says initial speed in meters per second, like you can see selected in blue on my screen right now. Hold down your shift key, then right arrow over to select hang time in seconds, and then use your down arrow key to select the initial speeds and the hang times. So that blue box now appears. If you look up in your formula bar here on the top left, it should say C2:D11 if you've done it correctly. Everybody good? Okay, let's now go to our insert menu. Insert your chart. Not what we want. There is a lot of stuff we have to change here. Please, under the setup on the chart editor, change the chart type to scatter, the one on the left. Now, for the data range, it should say C2:D11. On the x-axis, it should say initial speed in meters per second. For series, it should say hang time in seconds. Are we good so far? Okay, please go to your Customize section. We have to add titles to our chart and axes. So select the submenu Chart and Axis Titles, please. For the chart title, this is a graph of, and I put it in red, hang time versus initial speed. Hang time versus initial speed. Okay, select your down arrow. Let's go to the horizontal axis title. This is initial speed in meters per second. Okay, let's go to our vertical axis title. This is hang time in seconds. You can now collapse that submenu. I want you to notice that we do not start the x-axis at 0. We have to. So the way we get that is under the horizontal axis submenu. Come down and set the minimum value to 0. Now I have both a vertical axis and a horizontal one on my graph. That's under the horizontal axis menu. Collapse that. We now need to add our trend line, which is under series. Go ahead and select trend line. And notice the default is linear. Does linear look like a good fit? Looks perfect to me. We now have to add the equation, which is under the label. That graph is now complete. So you now can click on that graph and move it down into the shaded space below question 2. Okay, everybody set? Your graph should look just like mine. Okay, now we're going to do the same thing in step 3, but notice that in step 3, we are now making a graph of range versus initial speed. This one takes a little bit of work. Come on. Okay, go to the submenu that says horizontal axis. Set the minimum value to 0. Type 0 in where it says minimum. And now it should have the 0 on the bottom left. Everybody all set? Any other questions? Okay, this next one's trickier to make. We want the initial speed versus the range. Notice that those two columns are not adjacent to each other. This is where we need a little more work. Go ahead and select the initial speed in meters per second. Pull down your shift key, right arrow over until you get to range in meters. Now use your down arrow key with the shift key depressed. So that way the box from initial speed to the range of 25.70 meters is selected. In your formula bar up here on the top left, it should say C2:E11. Everybody have that? Okay, go to insert chart. And I'll show you how to customize this because again, it's not what we want. Under setup, change the chart type to scatter. The one on the left. Notice that right now we have a legend with both the hang time and the range given to us. We don't care about the hang time on this graph. So let me show you how to fix that. You notice your data range should say C2:E11. The x-axis should say initial speed in meters per second. Is everybody with me? Okay, come on down and you'll see under series, it's showing you 2 sets of data points, the hang time and the range. We do not want the hang time on this. So do you see how there's 3 dots on the right? Click those 3 dots to the right of hang time and say remove. Now we're just going to have the initial speed and the range on our graph. Okay? Now we can go to customize this. Let's start with our chart and axis titles. Let's start with the chart title. This is a graph of the range versus the initial speed. Range versus initial speed. Now select your horizontal axis title. This should be the initial speed in meters per second on the horizontal axis. Now you can do your vertical axis title, which should be the range in meters. Is everybody good? Okay, let's collapse this submenu. Look at the bottom left. Is the x-axis starting at 0? It needs to. Do you remember how to get that? We just talked about doing that. That's under your horizontal axis submenu. Set the minimum value to 0, please. Now it's what we want. Are you selecting the horizontal axis submenu? No. Okay, that's because you don't have the right type of graph. Did you already put a trend line on there? Yeah, you don't have things here. So go back to your setup. Okay, it's C1, B11. That's fine. Okay, so now that we have that minimum value of 0 there, let's now collapse that. Let's add our trend line under the series option. Linear is the default. Does that look like a good fit? Yeah. Okay, so let's add the equation to that for the label. And that graph is complete. We can now click off of that, click on your graph, and drag it down into the space for question 3 on this tab. Range versus initial speed. Okay? Let's go to part 2 and make the graphs now in part 2 because I think that's it for part 1, right? Yep, it says go on to part 2, effective height. So let's make our first graph now in part 2, which is hang time versus height. Okay, so what you're going to do is select the height here in meters. Height in meters. Hold down your shift key. Right arrow over to hang time. Then use your down arrow to select all of the data. If you look at your name box here on the top left, it should say B2 colon D9. B2 colon D9. Let's go to insert the chart. It's giving us the wrong type of chart again. The chart type needs to be what? Scatter, the one on the left. Okay, on the x-axis, we do not want the height. Actually, do we? Yes, we do want the height. Keep the height there for the x-axis. On the series, we do not want the initial speed. You can click those 3 dots for initial speed and say remove. We just want the hang time. Everybody good? Okay, so now let's go to the customize option. Start with the chart and axis titles. The chart title should be a graph of hang time versus height. Hang time versus height. Now let's go to the horizontal axis title. This should be the height in meters. Horizontal axis title is height in meters. Now let's do the vertical axis title. This is the hang time in seconds. You can now collapse that menu. Take a look at your x-axis. Is it starting at 0? It needs to. You remember how to get that horizontal axis to start at 0? Let's set it under the horizontal axis menu. Come down, set the minimum value to 0. I'm now going to collapse that. We're now going to add our trend line under the series option. Let's select the trend line. Linear is the default. Does linear look like a good fit? No. So since this is probably a curve then, what type of curve are we supposed to start with? Remember the name of that type of trend line? Which one of these do we select next? That is correct. Select power series. That looks beautiful. You see how it's hitting all the points? It's going towards the origin, which makes sense. If you have no height, you're not going to have any time. Let's now go ahead and add the equation for that trend line. We can now close our chart editor, click on the graph, and drag it down into the space for question 2. I'm going to make mine a little smaller so it does not cover up question 3. Okay, let's go to question 3. Number 3 wants a graph of the range versus the height. So we're going to come back up, select height in meters, hold down my shift key, right arrow over to the range. Pretty much we're selecting the entire table. Hold down your shift key, down arrow to select all the data. Go to insert chart. We do not want a bar chart. We need a scatter chart. Oh, lots of stuff here. We are going to keep the height on the x-axis, but come on down under series. The only thing we want here is the range. So please select the 3 dots for initial speed under series and say remove. Please select the 3 dots for hang time and say remove. All we want is the range. Now we can go to customize our chart and axis titles. The chart title is range versus height. Range versus height for the chart title. Now select your down arrow. The vertical axis title is the range in meters. Select your horizontal axis title. This is the height in meters. I'm going to collapse that. Notice my graph does not start at 0 on the x-axis, so let's set that under the horizontal axis submenu. The minimum value should be 0. Now I can go ahead and add my trend line under the series option. Linear is the default. Does linear look like a good fit? No. Let's see if we can do better. What should we select next? Power series, try it. That fits it perfect. So let's go ahead, add the label for use equation. We can now select that graph, drag it down into the space for question 3. And notice it now tells us to go on to the analysis where we're going to answer the questions. You ready to do that with me? We're almost done. Let's go to the analysis tab. Question 1, and we're going to answer these by referring back to our graphs and the data that we collected in each part. So the first question asks us, what effect, if any, does the initial speed have on the time of flight? So where did we test initial speed? In part 1. See, it says part 1, effective initial speed. So let's go there. Let's look at the hang time, which is the time of flight. If I change this speed, did that change the hang time? Okay, so let's go ahead and answer that question then. Under the analysis, changing the initial speed has no effect on the hang time. That's a complete sentence. We need to do these in complete sentences according to the directions. Changing your initial speed has no effect on the hang time. So what effect, if any, does height have on the time? So let's go to the part 2, effective height, and let's look at the hang time graph where we change the height. If I increase the height, is the hang time changing? How is it changing? Ryder? That's right. So let's go ahead and answer that. So increasing the height increases the hang time. Okay, question 3. What's the relationship between this horizontal fired projectile's initial speed and range? We have to look at that graph where we have initial speed and range. That's under part 1. So let's look at our initial speed and range graph, which is here. What do you notice is the relationship on this graph? Can you name that relationship? Miriam? That's a direct relationship, which means as the speed goes up, so does the range in proportion. So let's go ahead and answer that. So what is the relationship? We're going to say the relationship is a direct one. Or maybe it's better to say there is a direct relationship between initial speed and range. Direct relationship between initial speed and range. Okay, the next question asks you, what is the relationship between the height and the range? We're going to find that graph under part 2 because that's where we tested height. So let's go to part 2. Look at the graph of range versus height. What's the relationship here? Anyone know? What shape is that graph, first of all? It's a parabola. What's the relationship when you have a parabola? Miriam? Quadratic. Very good. So let's go ahead and answer that. There is a quadratic relationship between height and range. Okay, number 5 is an application question. Let's see if we understand what we learned. We have 2 toy trucks rolling off the same table. One is going at 2 meters per second, the other at 6 meters per second. Which one of them is in the air the longest? So based upon what we said, if I increase the speed only, does that change the time? That's question 1. If I change the speed, does it change the time? So what does that mean the answer is? Which one's in the air the longest? Ryder? And that's because initial speed has no effect on hang time. Which one lands further away from the table? That's the effect of speed on range. Let's go back and look at our graph. If I look at my graph of the range versus our initial speed, what do you notice as I increase the speed happens to the range? What happens, Elisa? It increases. So which one's going to go out further? 2 meters per second or 6 meters per second? Look at the graph. 2 or 6? 6, because that has a bigger speed. So the toy moving at 6 meters per second will land further away from the table. And that's because there is a direct relationship, as we answered in an earlier question, between initial speed and range. Right? Didn't we answer that in question 3? Direct relationship between the initial speed and the range. Okay, number 6, last question. You wish to launch a projectile horizontally, like we did in this lab, and give it the biggest or longest range you possibly can. You are only able to throw it at a maximum speed of 25 meters per second. What should you do to maximize the range? What should you do to make it land the furthest away? Look at the variables in this graph, in this lab. Speed and height. Those are the only things you can change. What should you do to make sure it lands as far away as possible? Ryder? And what else should you do besides make sure you are launching it from as high up as possible? One. which is what speed? Okay, that's correct. So to maximize the range, we should launch the projectile at its maximum speed, which is 25 meters per second, and from as high as possible. That's it. Once you've entered that, make sure you hit enter. So move out of that cell. So that way on the top right, you should see up here. You see there's a little cloud in the top next to the title. You should see a check. That means all your answers have been saved once you've moved out of the cell. Then go into Google Classroom and hit turn in. It needs to be turned in before tomorrow's class, okay? Have a great day, folks. I'll see you tomorrow.